So I think maybe before you talk a little bit about Novaloop, talk about the way most plastics are recycled that are not done by you, so we can sort of set the stage for like what the baseline is, and then we can talk about what you're doing differently.
Yeah, so the plastic problem is one that has been pretty much a sleeping problem for many decades. Before 2018, we didn't really even talk about it or hear about it because we were exporting, California especially, was exporting almost half of its plastic out. Actually, I think more than that, 60% or so out to China, because the shipping containers would go back empty, right? So America, over the decades, have built itself up to be very good on focusing investments based on jurisdiction, local city level, to be good at separating materials. So we have material recovery facility technologies that separate cardboard, metals, glass, plastics, and then we offshore everything. So if you're in the East Coast, in the middle of the country, we do have some recycling, but most of the plastics, if you're looking at a lot of the commodity plastic waste like polyethylene, that material, the biggest takers of it is Trex, the company Trex. They make plastic lumber decking boards, and they're taking that material and they're grinding it up and using an outdoor kind of decking boards. So it depends on which waste stream we're talking about. Plastics are many waste streams. The highest recycling rate waste stream is PET plastic, which is used to make clear water bottles. That material can be used, you cannot turn it back into food grade, but you can use it in some other PET applications. But you have so many different plastic waste streams. You have the PETs, you have high-density polyethylene, low-density polyethylene. High-density is what makes the milk jugs. Low-density polyethylene is what makes the shopping bags, which we've tried to ban, but it's not banned. We have bans on the ban. So, literally, this is a thing, and every state is different, but you still see them everywhere. You have polypropylene, which is all the food takeout containers, and it's full of grease, very hard to recycle. So the overall issue is, less than 9% of plastics globally is recycled. In the U.S., I would say, depending on which region you are, especially in the West Coast, recycling of plastic is even harder because we're kind of farther away from, places like Indianapolis, where a lot of the recycling kind of takes place. And so if you're looking at the waste stream that we focus on, which is the most abundant polyethylene, so that's low-density polyethylene and high-density polyethylene, makes up more than a third, or over 100 million metric tons of material globally every year. The U.S. recycling rate on things like low-density polyethylene film, so that's things like plastic bags, on a post-consumer level, which is after a consumer uses and throws it away, the recycling rate of that is less than 5%. It's around 3%, right? So most of it's just going straight to trash. And the main issue behind all of this is that we're not even collecting the stuff or sorting it because the virgin prices are so cheap. It's so cheap to make this stuff directly from the ethylenes, and we have so many of these plants and so many projects constantly being added. And so this is not just a U.S. problem, it's a global problem, but America has another issue on top of this, which is that it's cheap for us to landfill, which is kind of unique. In Europe and in Asia, they don't have enough land. They burn everything. It's kind of expensive to landfill. So they are naturally inclined to do more recycling, pay more. Even before, currently they have new legislation rolled out in November banning export of plastic waste beyond the EU boundaries. Previously, before this is in place, they already had in every neighborhood, people have to walk down to the street to bring their recycling and separate it themselves by hand. We don't have anything like that here. And we think landfilling is a form of carbon sequestration, right? So it's very hard.
I mean, technically,
yeah, but is that what we should be doing?
Yeah.
And how, then you come into this conceptual challenge, right? Because right now, things like the IRA are specifically targeted at hard-to-abate sectors. Bill Gates wants to invest in technology that will offset 500 megatons at least of CO2 per year, right? Or by 2050 they can achieve that. Plastic currently doesn't fall into that, right? But is it a smaller problem than cement and steel? I mean, you're much more likely to see plastic waste out in the environment than I'm not saying it's not hard to see the waste. A lot of that is kind of invisible to the consumer, right? But the plastic waste is a huge pervasive problem for us. And so, it's kind of right now falling through the cracks if you look at how these current legislations in the US are. In Europe, they're actually putting a legislation and they're enforcing you have to have certain percentage recycled content. So it's really interesting to see internationally the dynamics here. And as a startup company, so we're navigating through this and learning how to scale up, is a particularly interesting time.
Yeah, so we are going to get to what Novaloop does differently, but I think since you brought up the IRA and talked about a startup, and we talked about it earlier, you expressed some frustration that as a startup with a novel solution that can really scale, but you need the right resources, and that money doesn't seem to be flowing.
Yeah, I think the challenge, the pain point in the plastic circular economy space is, especially in the US, but it's a global policy challenge, is that you don't really have people seeing eye to eye on the exact, how would I put it, the chemical recycling as a term is extremely controversial.
It sounds controversial.
It sounds very controversial because it's traditionally referred to plastic to oil technologies, where technologies that are taking plastics and heating it up to very high temperatures and turning it into a kind of bunker fuel, like low quality oil, which then you put through a refinery. This technology has been around, developed before World War II. As a way to sort of cycle plastics and find some way to get some value back in the day out of. But nobody has been scaling that because you get such like bad quality products, waxes, these branched, oils, very hard to use this stuff, inconsistent. But recently, because, 2018 onward, there's been a lot of talk about, what about plastics? Everybody starts caring about plastics. Big chemical companies, oil and gas companies are also looking at how more and more of their income is going to come from plastics and not from energy, selling oil for energy, right? And they're looking at how to keep the steam crackers on, right? And this technology is now being revitalized, right? Brought to the surface. And all these names, chemical recycling, advanced recycling, molecular recycling, all these names. And what they're doing is making these branch oils so they can feed them back into steam crackers at a small dilution to virgin oil to make plastics. And so this technology, I'm not saying here it has no place in the world, but it is what the big oil and gas companies are going for. And
basically, they're still oil companies. They're just taking the plastic and turning it into more oil and running it through their system again, which is never going to be clean.
Yes, and the issue with this is that it actually has a larger CO2 footprint if you take plastics and put it in high temperatures to make oil, and then you turn that into plastic, and that has a higher CO2 footprint than just taking oil out of the ground. So, right now, that's why it's controversial. But there's actually a whole lot of new innovation right now coming out. Silicolysis, using solvents to clean plastics, technologies that are like us, we're actually breaking apart and decomposing the plastics by oxidation with very low temperatures. A lot of these technologies right now, there's a lot of textile recycling technologies using some combination of these, these methods. And we're kind of grouped in this whole bucket that policy feels kind of confused about.
So talk about like what you're recycling and then how you're transforming it, and then we'll get to what you're doing with it at the end. But like, what types of plastics are you taking, and then how are you changing them?
Yeah, so what we focus on is polyethylene plastic, I mentioned, is the most common one out there, very low recycling rates. And we invented a technology that oxidizes the polyethylene. So we take things like shopping bags, we put it in conditions below 150 degrees Celsius, low temperature, very short reaction time, and we break it down into short chain chemicals. So, polyethylene is a very long linear carbon chain, very boring. There's not a lot of reactivity to it because they don't have any other function groups really. And so what we do is we oxidize and we cut up this carbon chain into smaller oxidized species. So it's not oil, they're not a bunch of long oil structures, it's oxygenated, which means that they can be purified and directly used as building blocks. So what we do is we make these monomers, and then we purify them and we build them into performance materials. So that's the key point, is we're not making the same plastic that was used in that shopping bag. We're not making polyethylene again, but we're making polyurethanes, for example, as a category of products. And so the materials we make are worth up to 30 times more. And so by naturally upcycling, you're upgrading, we call this process life cycling, you're able to build a technology scale-ups that are much smaller, like at 5% the scale of today's fossil fuel-based processes. We're at 5 times scale, but we have similar unit costs. And so, because we're leapfrogging about 5 or 6 steps of synthesis. We're not taking the plastic, going to oil and going through the supply chain. We're going straight to an intermediate compound and building from there to higher end materials. And so that's what we do. And we have been working on scaling up this technology. And this is something that you and I were talking about. As an American startup based in Menlo Park, developing this from the laboratory research stage for 9 years, it's always been my dream to be able to build this scale up in the US. But it's so hard. It's so hard to establish manufacturing here. You know, I can go on and on about this,
well,
but it's very, very hard.
You've hit a couple of points. One is that we have a history of exporting it, and exporting it isn't that expensive because the boats are already flowing that way, although not everybody will take it anymore. Then there's the landfill temptation, which we've got plenty of land, and it is a form of sequestration. So and it's cheap. So that you're competing against that too, and the difference being in the regulatory environment in Europe, they have to keep it there. They can't ship it out, and we don't have anything like that here. And so maybe talk a little bit about like what are some of the other options that you're looking at, and what makes them attractive compared to us, other than those two things.
Yeah, so you have Asia, which naturally, if you're looking at countries like India, you know, you have excellent engineering talent. You have people who speak English. And you have people who cost a tenth of the cost here for labor, right? When you're looking at, from a CapEx total installed cost standpoint, anywhere in Asia, like Southeast Asia region in general, you're looking at about a third of the cost compared to the U.S. building the same plant in the U.S. Same scale, same capacities. In Europe, your CapEx is a little higher than in the US, and labor is high, but they have a lot of government incentives, right? Like if you're looking at countries like Finland, they have money that you can easily apply for and get from their governmental entities because they already have requirements. You have to be pretty serious about building there before you apply. So the competition is not extremely high if you're really committed to doing it in that country. And to them, even if you can recycle 20,000 tons of material a year, that's significant to their nation because they're not so big in population, they'll make so much waste. And they have all these EU regulations where they have to recycle, they're at 35%, moving on to 55%, and they actually get fined every year as a government by the EU if they don't hit those recycling rates. And so in their minds, their local governments are thinking, I either invest and attract foreign technology to come and build, scale-ups so that we can actually create new jobs and we can recycle materials, or we have to pay fines over and over again for failing to meet those targets. So, it's hard to make a justification for that from an IR standpoint. And then you have timelines, right? In Europe, your timelines are long to get these projects. In the US, they're long too. In Asia, it's very, very short, depending on where you're going. Lots of people you can partner with who have the land and everything that you can work with. So it's, of course, project dependent, but these are my observations.
Yeah, well, I think Novaloop is moving pretty fast, and I think you're going to wind up building that plant somewhere else. That's just my guess. We're about to go into another break, but I want to open it up for questions.
Yes, I'd like you to talk a little bit on the sourcing of the material. So plastic, as I understand, is difficult to recycle because they're all different, and you talk about plastic bags, but is there like a specific kind of plastic bags, for instance, that you would take and not others, and how would you figure out that part?
Yeah, so there's a lot of technology already and more that's growing quite fast in terms of sorting and identification of materials. So traditionally, material recovery facilities are technologies on plastic use optical density sorters, right? So you shine a light, you figure out what, based on the density, what kind of polymer it is, use air to eject it. All material recovery facilities in the US essentially have this if it's of a certain scale. But now you have AI technologies, like companies like Amp Robotics, they have AI robotic arms. They're extremely efficient at picking things apart and sorting them. And so for us, we're specifically, because we're using a chemical process, we're specifically looking for polyethylene. So polyethylene has many different densities, many different forms. It can be, everything, high density polyethylene is, rigid plastics, things that are used, like I mentioned, the milk jugs, for example. That's a higher value one that we wouldn't really go for. But all the way to things like agricultural plastics, like the black plastic tarping that's used to line and mulch all the strawberry fields out there, right? So we want to go for the lower value things that are usually highly pigmented, so mechanical recyclers don't want to use them today. If they use a black plastic to start, then they can't make something of another color. They can't even make something that's red in the second generation, right? So we're going for something that naturally have lower marketability as a plastic waste. And then we source it as a pellet, which means that we actually are buying it from a middle processor. So somebody who is taking a bale of, say, agricultural plastic sheets, right? And then they're putting it through a shredder, an extruder, and then they end up generating a bunch of black pellets out of it. We buy that from them. So we are not set up, we're not interested in doing all of these steps that are not focused on our core innovation. And so by doing this, we are creating new markets. We're creating new demand for plastics that otherwise nobody would want and therefore would not move.
And some of the products you're creating, I think running shoes and sneaker soles are on the website. Like those are the types of plastics that your end product that you're then going to sell to.
Yeah, so we're taking polyethylene, which is, values like $1 a kilogram or so, and we break that down and we build it up to a thermoplastic polyurethane, or a TPU, material you might not heard of, but it's in your phone case, for example. You might be touching it right now. It's in the bottom of your shoe sole. It's the material that allows you to, have the comfort for a long time, It's in parts in a car. It's a lot of these durable goods, right? That material is worth, somewhere between $5 to even $7 a kilogram. And so, we're making these polymers that inherently have technical performance, right? It's kind of engineering grade plastic, have technical performance. So when our customers want to adopt it, they have to test. So this is another interesting thing, is that we've specifically gone after applications where it's not like anybody can easily get into it with a new material, right? So our materials, usually a customer testing it out, go through a handful of ASTM tests. So for example, they put it in an oven at high humidity and see over 60 hours, does it change color? Like, they go through stuff like that to determine if it's good for an escalator handrail, right? So when you are in a category like that, 99% of the market share is fossil-based, 100% virgin material, and 1% is bio-based. But the cost is so high on bio-based materials. And so we are positioning ourselves as the only sustainable alternative that's also not going to cost that much more. We're going to be at close to parity for the compared to the fossil-based products, and with the same performance, because our material is virgin. We're building it up from the same, breaking it down to the building blocks and building it up from scratch. So these are the kinds of new approaches I'm talking about, in my category, which I think a lot of the times is hard to notice it. Because if you look at, for example, what the IRA most recently, last week, they announced the Industrial Demonstration Program projects. $6 billion was deployed and attracted overall between public and private funding $20 billion, somewhere around 40 to 60 projects may be identified across many different hard-to-abate areas. In the petrochemical area, all the funding went to public companies, public and oil and gas companies, and all of them were carbon capture related. So you have an ethylene plant, you bolt on something that captures, the emissions. Basically, all of that was that, and except for one, which was Eastman Chemical's PET recycling glycolysis. They've had that for many years already, right? And it's not really like startup level kind of new innovation. And they also, you can say they have funding. They should have the funding to build that themselves, because it should be a profitable process, right? So.
Well, I think you've got, you may not have gotten the government's attention with the IRA, but you certainly got the attention of the people in the room here. And I think you've made a very strong case. Thanks so much for talking to us today.
Yeah.
Thank you.
Thank you, Dan.